Good afternoon. My name is Rohit, and this is Teja, and we're here to present before you Helios technology, also formerly known as interpixel photovoltaic cells. Now, in our presentation, we're basically going to cover we're going to cover the following details: the basic scenario for our design project, the design concept and fabrication, as well as the materials that we are selected, the fabrication methods and the characterization that we followed, and any issues and failure analysis that were done. In addition, we are also discussing some of the future plans that we will be considering, followed by acknowledgements and then questions. Now, the basic scenario for our design project. Over the past decade, mobile technology has largely evolved, and we see devices with amazing specifications, such as the processor capabilities that surpass largely what computers could do past few years. Displays with pixel density so high that they're invisible, that it's invisible to the human eye, and cameras with capabilities that can replace standalone devices. But the one area that hasn't seen major improvement is in battery technology. Over the past decade, what we're seeing is that there has been degradation in the battery improvement. That's mostly because companies haven't been able to keep up with the pace of every other technology improvement that's been happening. So our design project was focused on trying to address this issue. Now, to do that, the first thing we did is try and focus on displays. Now, generally, displays are made up of red, green, and blue light-emitting diode, and the combination of these three colors can produce any color that you want. Now, recently, some companies have introduced the concept of having a fourth subpixel, which is white or yellow in some cases, and it's for color saturation, and they also claim power savings. Our team felt we can use this existing design principle, but instead integrate solar cells in place of the fourth subpixel. What this means is it can occupy the same area as the previous existing display design. So it maintains the pixel densities that's current industry standard, and it can also maintain the display quality, since the photovoltaic cells are only 64 by 16 microns. So it's still invisible to the human eye at a distance of approximately 6 inches. So what this means is that anytime your device display is active, or anytime your device is exposed to ambient light, the solar cells in the display can harness this light energy to charge your device. And since we're integrating it into the display, there is no additional layer that is required, so it maintains the display quality. So there's no light loss that's happening by the introduction of an extra layer. Now, the project goals for our design project were the following. The primary goal was we wanted to miniaturize the solar cells at the micron scale and achieve a 16 micron wide solar cell structure, such that it's invisible to the human eye at the specified distance of 6 inches. Our secondary goal was to develop an array of photovoltaic cells and integrate it with a passive matrix OLED, so that we can actually show that it's capable to actually fabricate both the OLED and the photovoltaic cell on the same substrate. And the tertiary goal was to integrate in an active matrix OLED display, which would be a regular mobile display. Now, the basic fabrication design of our design project is as shown. We wanted to try and fabricate our solar cells on a glass substrate. And as part of our tertiary goal, we wanted to be able to do it in such a way that we can actually fabricate the OLED on the same substrate that's shown here. Now, in the following slides, we're going to discuss about the materials that were used.
Okay, for the substrate, we decided to use Corning glass because it provides optimal transparency at the visible wavelength. And it also allows for a process temperature window up to 500 degrees C, which is approximately what we need for the processes we're going to be using. For the cathode, we chose to use aluminum because it provides great electrical conductivity, which ensures that we have minimal resistive losses because of sheet resistance and other factors. And it also has a decent thermal conductivity, which ensures that our device does not heat up beyond a certain measure. And also, it's a low-cost product. For the photovoltaic cell, we chose to use amorphous silicon because it provides a decent conversion efficiency at a very good current cost per watt. And also, it's not a toxic substance, which means it can be handled using, say, regular laboratory procedures, which is ideal for us because this will be one of our first times working at a fabrication facility. And also, it is fairly reliable and doesn't degrade as fast. For the anode material, we chose to use aluminum zinc oxide over ITO because though both of them offer a good amount of transparency, ITO is known to degrade very, very much faster. So this ensures that we don't need to do anything extra to ensure that our product isn't degrading, such as like nitrogen encapsulation or other such factors. When we can transfer the product from one place to the other. So our PV fabrication process, the anode and cathodes were done through sputtering, which is ideal for this because it provides us good step coverage, and it also allows for us to use a low process temperature, which is ideal for some of the materials we're using. The photovoltaic cell itself is amorphous silicon. It was deposited using PECVD, and we did the p-dope silicon by introducing trimethyl boron and silane gas. And then the n-dope was done through phosphine and the silane gas again. And we chose to use this process because it has high efficiency for multi-chamber processes, and it is also ideal for, it works at a process temperature of about 300 degrees C, which is ideal for the materials we're using. We did our patterning using like contact lithography with a silica shadow mask. And also our silicon, to etch the amorphous silicon, we used SF6 plasma for reactive ion etching because this provides a good anisotropic etch of the silicon. And also we did our aluminum etching through KOH. Okay, so for our characterization results, our dark IV measurements show just diode characteristics, which essentially means that the contacts were fabricated as intended, and there was good contact between the silicon and the aluminum and the AZO. Our PV cell characterization shows like an expected IV curve that we expected from the solar simulator. And for our parameters of interest, we achieved a shunt resistance about 1.36 megohms, which is ideal because a high shunt resistance allows for minimal current loss. Minimal internal current losses. And we also achieved a maximum power of about 76.6 microwatts per centimeter squared, which is again around the area what we expected. We did our biggest downfall for this prototype was that we got a very small short circuit current, which was about 0.12 microamps. And we got about 0.4 volts. 0.4 volts as open circuit voltage and a 26% fill factor or 25% fill factor, which is again as expected. So the complications with our design were first that our IV measurements indicate a much lower quantum efficiency than what we expected from amorphous silicon. We were expecting somewhere around the 5 to 6 range, but what we got was much lower than that. And we also got a very low short circuit current. And as for possible explanations for this, we think that the biggest issue was the AZO deposition process with the sputtering. And this process was not very even, and we think that's why the sheet resistance of the AZO is much higher than what we expected it to be. To continue with this, we plan to do a Hall measurement to determine the mobility of the AZO sheet, and this will allow us to continue further. Also, silicon contamination is a big issue because for our product, we went through several labs to do it. We did the PECVD and ERC lab, and we did the aluminum deposition in another lab. So in between this, we were transporting the wafer itself just in a case, and we think this led to a lot of contamination issues for the silicon, and which is why our efficiency was not as high as expected. And we plan to improve this by doing secondary ion mass spectroscopy to determine what possible impurities we find. And we also decided to counter this issue with using nitrogen encapsulation during the prototype transport.
Now, looking back at our project goals, as per our design project, what we were able to achieve, where we were able to achieve all of our primary goals, such as we were able to actually miniaturize the solar cell at the scale that we wanted to, the 16 by 64 micrometer scale, and this ensures that it's actually invisible to the human eye at a distance of 6 inches. We have a sample that's in display, so you can drop by if you want to actually see it. And as part of a secondary goal, we were able to develop an array of photovoltaic cells. So we were able to do it on a single substrate and able to get good fabrication results out of it. But there were a lot of issues associated with the deposition. So we didn't get to the other aspects of our secondary goals, such as the OLED integration with the OLED. And we are considering that as part of our future plans for to take our project further. And now, to discuss our future plans, the first thing that we're considering is actually investigating other materials that we can possibly consider. As you know, amorphous silicon, it has a good, the performance versus cost is justified, but we believe we can get better performance by considering other materials such as crystalline silicon or organic solar cells. We are looking at that. This will also help us improve our quantum efficiency and also help us perhaps achieve a better performance versus cost. The second part of our future plan is to actually implement our design with a passive matrix OLED. So what we want to do is to be able to deposit a monochromatic OLED through thermal deposition. The reason why we're going to use thermal deposition is thermal evaporation, sorry. The reason why we're using is because it gives us precise control over the deposition of the OLED compared to spin coating, and it's also widely used in the industry for display manufacturing. And the third part of our future plan is we want to design a circuit and interface for a dual battery system. What this means is we would have a primary battery and a secondary battery, so the solar cells can constantly charge the secondary battery. So when your device is not actively being used, the secondary battery can power your device, because at the low power state, the secondary battery would have enough potential to drive your device. And the last part of our goal is to actually develop a full prototype device with RGB display in it. So this would be reflective of what it would look like if we were to integrate it into a mobile device. And that's the final part of our future plan, and that is Helios technology. We would like to acknowledge the Energy Research Center, Dr. Mansour's group, Dr. Siva's group, and Dr. Hani Aziz's group for the help that they have provided us. And we're now open to questions. Thank you.
Because the miniaturizing of the PV cell, like, it reduces the surface area, so overall, like, the amount of current we're going to be generating is much less. But because of the fact that there's way more of the smaller solar cells, we think that would counter the issue. And also, there's a higher amount of sheet resistance involved when you have contacts that are very small as well. And that again has to be improved overall by trying to look at different materials and other things we can do to counter that issue.
All right, if there's no more questions, let's
Okay, we're done.
again.
All right. Thank you.